size of two-colorability, and we want to explain to you.
Thank you. So thank you for staying for the last talk of the entire conference. This talk is, however, not about crochet distance or similarity in any way possible. Okay. So let me start by defining two-colorability. Okay, so you're given a hypergraph, and you want to color the vertices using two colors, red and blue, so that no edge is monochromatic, meaning that it contains vertices of both the colors. Okay, so that's what being two-colorable means. Now, we are probably familiar with this concept in a slightly simpler setting, which is the one of graphs. So let's say your hypergraph is a simple graph, meaning that every hyperedge is an actual edge of size 2. Then two-colorability is just the same as bipartitions, for which we know that there is a nice polynomial time to compute that. But that similar thing is not true for general hypergraphs. So it is indeed incomplete to determine if a given hypergraph is two-colored. But here is a very nice intuitive phenomena that happens. So suppose your hyperedges are very large.
Yes. General hypergraph means bigger than 3.
Yes, more even.
Even 3 is NPR?
Yeah, even 3 is NPR. That's the result of the watch. I'll mention the incrementation. So coming back to this, if your hyperedges are very large, meaning they contain a lot of vertices, then you can, let's say you do a random coloring. For each vertex, you decide to randomly color it red or blue. The chance that you remain, that an entire edge remains monochromatic is very small in that case. And indeed, Erdős formulated the result giving the best, or giving some sort of quantitative formulation of that. If the number of edges is at most 2 to the p minus 1, and each edge is of size at least p, then the graph is two-colorable. Better results are known now, but this is the result. Now you'll have to absolutely trust me that I tossed a coin to do this coloring, and it indeed came out to be two-colorable. So this was a random color generated for this hypergraph. Okay, so why did I bring this up? So let's look at geometric hypergraphs. So let me just define that in a couple of slides. So how are geometric hypergraphs defined? So we take a set of some endpoints, and we intersect it with a given class of figures. For example, the set of all disks or all parallel rectangles and so on. And the points and whatever one of the rectangles contains, those points form a hyperedge. For example, there are 3 hyperedges here. But I have not shown all of them. There are more, obviously. And then there is another kind, which is known as dual hypergraphs, which are defined by a finite class of figures, which you look at their arrangement, and then you take a cell of the arrangement, and you look at all the figures that contain that point. So that defines one hyperedge. And again, I have not shown all the hyperedges in this in this collection of figures. So the nice property about geometric hypergraphs is that the number of edges is not too large. So here, if they're defined using n points or n figures, then the number of edges is at most n to the d, where d is the shattered dimension or some small, which is usually some small function of the dimension. Okay, so it's at most polynomial in some sense if the dimension is constant. And therefore, if out of that hypergraph, we only look at the edges which are large enough, meaning that the size of the edge satisfies this, then the sub-hypergraph of such edges will be two-colorable. So it turns out that if the edge size is at least log n, then the hypergraph is two-colorable. Okay, so here is where we define a parameter lambda of what we call the threshold of two-colorability for the hypergraph to capture this concept. So let's say you're given a hypergraph h, and you fix an integer t, but you look at all the edges of the hypergraph which have size at least t. So the problem is, so lambda h is defined as follows: it's the minimum value of t for which this sub-hypergraph is two-colored. And clearly, if you fix t equal to the size of the vertex set, you have only one edge, and therefore such a hypergraph is two-colored. So there exists such a minimum t. And one can observe by a random coloring argument entirely similar to the one by Erdos that in fact lambda edge is always bounded by the logarithm of the number of edges. So here are the main questions that we consider in this paper and try to answer them. So lower and upper bounds on lambda edge, what can we say about this for various hypergraphs, in particular coming from geometry? Can we efficiently compute lambda edge? But that is already known. We cannot, as I mentioned, it is even NP hard to determine for a 3 uniform hypergraph if that is 2 colorable, meaning its lambda edge is equal to 2. So the next question would be, can we efficiently approximate it? So here's the result number 1 of this paper, is that it is indeed hard to approximate this even logarithm of the number of edges. So there is some constant c bigger than 0, such that if I ask you to output a number alpha that lies within lambda j or c log n times lambda j, this problem is NP hard. So what that means is, and this follows from a reduction of determining whether a 4 uniform hypergraph is 2 colorable to a gap version of our problem. So the details are not that interesting, so let me leave this out of this talk. But what that means is, so if somebody asks you what's the value of lambda edge, you can simply output logarithm of the number of edges, and this in some sense is an optimal efficient approximation unless we. So there's nothing better you can do other than a random coloring in the worst case. Okay, so before I go on to talk about lower and upper bounds on lambda edge, let me just give some definitions about what we mean by families of hypergraphs. So in families of hypergraphs, for each n you have some hypergraphs with n vertices. So for example, you have primal geometric hypergraphs defined on n points, or dual geometric hypergraphs defined on n figures. And so the main questions there are, so if I fix a class of figures, for instance, that defines for each n a lot of primal hypergraphs, so how does this lambda edge depend on n? And as we have seen, for geometric hypergraphs, we can have this easy upper bound. So is there a corresponding lower bound? And it turns out that results in the absolutely fantastic area of cover, decomposability, and indecomposability imply lower bounds for lambda edge. So to have a 2-minute introduction to this area, so what is cover decomposability? So you fix a class of figures. For example, for this here, it is unit disks. And let's say you have a sufficiently deep covering of the plane, meaning that every point is covered, say, 10 times. Then it's intuitive that you can split that covering into 2 coverings, where each one of them into 2 distinct or 2 disjoint collection of figures, where each of them is a covering. Now that is not always possible. That's very counterintuitive, but that's actually the case. It's not always possible, and that's what proving cover indecomposability is about. But there is also the equally fantastic problem of proving that some set of figures is actually cover decomposable. But results in cover indecomposability actually help us to prove lower bounds on the corresponding dual hypergraphs that are defined. So typically, the way they do that is they prove that a certain bad hypergraph that is not 2 colorable can be realized by the class of figures. Okay, so here is one example of such hypergraph, which was introduced in a paper of Pach, Tardosh, and Todd, which is one of the first papers to deal with indecomposable coverings, or first modern papers to deal with that, which is defined using an arbitrary tree. So you take any tree, and it doesn't have to be regular like this one. And then there are 2 kinds of, the vertices are all the vertices of the tree, and there are 2 kinds of hyperedges. So one are the sibling hyperedges, which are just all the children of an internal node. And the other are the hyperedges defined by root to leaf paths. And it is actually easy to see that this hypergraph is not 2 colorable for any tree. Okay. So in their paper, Pach, Tardosh, and Todd realized this hypergraph for a specific kind of regular trees by various geometric figures, and they were able to prove that the coverings are indecomposable. So there are many other such constructions known, and in particular, Paldolgai have come up with another hypergraph, which I have not shown here because its definition is more complex, and realized it by various figures, both the primal and the dual. When I say lambda h star here, it stands for the dual hypergraphs defined by those figures. But here is an example of one lower bound that follows from their constructions. So for open unit lists, for example, we can prove that both for primal and dual hypergraphs, we have lambda h and lambda h star is omega log n. So what that translates to is the following. So if you, let's say you're given a set of points in the plane, then no matter how you color it, there exists some set of points in the plane such that no matter how you color it, there will always be a disk that contains at least, say, log n by 1000 points that is monochromatic. So that's what this lower bound means. So in their paper, Indecomposable Coverings, Pach, Kardosh and Toth had tried to prove or try to establish this sort of thing that the hypergraph of axis parallel rectangles could possibly realize this particular hypergraph. And they left it undecided. They proved that for their purposes, they only wanted to prove that lambda h is not a constant. They achieved it through other means. However, they left this question undecided whether this hypergraph could be realized. And in this paper, we show that indeed it cannot be realized. And I also suspect that the other hypergraph that Kumar used also cannot be realized, but it is not something that we have been able to show. So let me give you in the next couple of minutes an idea of how we prove that this hypergraph cannot be realized. Now, the hypergraph about which they were really interested is the tree Tk, which is defined as follows. It is a very regular kind of tree. It has depth k, and every internal node has k children. Okay, so that's the tree that they were working with, the class of trees. And they showed that some figures can realize every tree in this class. So in fact, what we show is that T5 cannot be realized by axis parallel rectangles, but we have a smaller version of T5, which is not really T5, but where nodes having depth 4, which are the nodes whose children are the leaves, have only 2 children each. It doesn't matter, you can make them have 5 children each as well. So that shows that for sufficiently large k, HTK cannot be realized as well. And the proof is by contradiction. We assume that a realization exists, and we somehow show that you cannot really pack up the tree in the thing. So it's really a packing argument which takes. So here's a piece of the tree that is shown here. This is to just introduce some notation. We let the root node be denoted by P, and P will also denote the point in the plane which it should correspond to. And then its children from the left to right are P1 to P5, and say for P2 the children are P21 to P25. So we can place P at the origin because it doesn't really matter, and we need to place the other points now in order to realize our hypergraph. So let's try to put the points P1 to P5 first, and the only criterion is that there must be an axis parallel rectangle which intersects those points just in P1 to P5. Okay, so that it should not contain the origin in particular. So because that happens, it must be the case that the points P1 to P5 cannot be in opposite quadrants. So they cannot be in 1 and 3 or 2 and 4. So again, without loss of generality, we can say that they are in quadrant 1 and 2. So at least 3 of them must belong to one quadrant. So let me call that quadrant, say quadrant 1. Okay, so I've renamed things to call that quadrant 1. And I claim that they must be placed somewhat like this, which is to say they are on the skyline. They're not comparable to each other. So when we say 2 points are comparable, we mean they are coordinate-wise. One of them is greater than the other in both their coordinates. Otherwise, we call that we say that they're on the skyline. So I claim that they must be on the skyline. And why is that? Because if you think it should not be very clear I mean, there are these kind of hyper edges, the root to leaf paths that go through, say, P2, and then there are corresponding ones for P1 and P3. So those contain the origin and P2, or contain the origin and P1, but don't contain the other points. So the points P1, P2, and P3 must lie on the sky. Okay. So with that, I claim that for the middle point P2, all the descendants of P2 cannot possibly lie in the first quadrant. Okay. And why is that? So this is by a simple case analysis. So let's try to see if I can place a point of a descendant of P2 in this gray rectangle. Well, it certainly cannot be in the gray rectangle because that gray rectangle defines this hyperedge. And that should not contain any descendant of P2. And that gray rectangle does not exactly define that hyperedge, but at least it's contained in that rectangle, which defines that hyperedge. Similarly, any descendant of P2 couldn't possibly be here in this rectangle because that defines this hyperedge, or is contained in the rectangle defining that. And we rule out this portion as well. It cannot be in this portion because otherwise the rectangle that contains P2, that descendant, and the origin will contain P1. So in other words, every portion of the plane of the first quadrant is ruled out. And so we push the descendants of P2 into other quadrants. It turns out that, therefore, the final diagram after this is done, this argument is applied at all levels, looks somewhat like this, where after we saw that the descendants of P2 cannot go into the first quadrant, they go into some other quadrant, so we assume that maybe that's quadrant 2. Doesn't really matter, it could be 3 or 4 as well. But if they go on to quadrant 2, because again there are 5 children, we can make an argument similar to that. There's a middle point here whose descendants must go to a different one. And when you have used up all the 4 quadrants, there is no way to place the children at depth 5. Okay, so that shows that that particular hypergraph cannot be realized using axis parallel rectangles. And that's a contradiction. So I'm almost done here. So to summarize, we have a definition for lambda edge in this paper and a hardness result for approximating that. And you observe that there are some lower bounds which follows from known constructions in the cover indecomposability lecture, literature. And we showed that a well-known hypergraph, the tree one, cannot be realized by axis parallel rectangles, but it would be nice to show that lambda edge is logn. This is, as far as I know, still open for the hypergraph of axis parallel rectangles. And this problem, it seems, is particularly hard because this would be another proof for what is known as Snelli's lower bound for the discrepancy of axis parallel rectangles in the plane, which is already a known result, but all known proofs are rather extremely clever. So so what it turns out that if we go by this way, using results in covering decomposability to prove this, it would have to have some sort of new ideas to be done. And that's all. Thank you.
Any questions? Okay, I think that's it. The end of the conference. Thank you all the speakers.